All right, welcome everybody. Let's get started here with a few announcements. So first of all, your next homework assignment is due on Thursday the 28th. So you've got some time to work on that forces on curved surfaces assignment. Now you'll notice that that assignment is due the same day as we're having the exam. So unfortunately what that means is you're not going to have your graded work back before you actually take the test. And so my suggestion for you is if you have any uncertainty on that assignment, let me know. If you're checking the answers with your classmates and everybody gets about the same thing, then you can feel pretty confident that you did the problem correctly, even if you haven't got it back from the grader yet. But if there's one where maybe there's a divergence of opinions or there were so many steps you're not sure if your answer's right, you can stop by my office and check the solution to make sure you've done it correctly, and I don't mind that one bit, since there's not time for you to get your graded work back before the test. All right, so for the exam itself, I've already posted the equation sheet online. It's on MU Online if you want to have a look at what formulas are going to be provided. And if you think there's an equation that you might need for the types of problems that we've been solving, but it's not on that formula sheet, then let me know. I think it includes everything you need, but I might have overlooked something. So the exam is going to cover lectures 1 through 11, so that includes not only this lecture, but also the one on Thursday and Tuesday of next week. It'll just be 75 minutes long. We'll have it here in the classroom, and you don't need to print the equation sheet that's online. I'll print that for you, but I put it on there just so you can get familiarized with where the formulas are, and if you want to, in your mind, review what some of the variables are in the equations. So any questions so far? Yeah?
Can we make our own equation sheet or?
No. Well, yes, you can. You just can't use it on the exam.
Okay.
Yeah. Who am I to say you can't do things, right? Don't let me stand in the way of your dreams. But I get what you're saying. You can't use it during the test. So one other announcement that is related to the lab. So if you haven't installed the software on your own laptop, please find a computer maybe from a classmate. I'm just curious, how many of you have successfully installed WaterGems so far? Okay, good. The real problem solvers are already on top of it. Now, you've got until today at 2. The first group are going to be coming into the lab at 2, and then 3:30, and then there's some tomorrow. But I hope that you'll get that installed. There's really not any point of coming to lab if you don't. So, anyways. All right, well, let's talk about hydrostatic forces on curved surfaces. And the way that you can start to think about how to solve these problems is what sort of a shape is made by a shadow. And so if you have a basketball, we know that a basketball is a sphere, right? But it looks like a circle. It's not actually a two-dimensional object. A basketball has 3 dimensions. But when you look at a projection of it, it's flat. And so this idea of, people do shadow animals just by rearranging their hands. It's the projection of some object, and you can project in different directions. But the way that we're going to find hydrostatic forces on curved surfaces relies a lot on understanding what the projection of the curve looks like. All right, so here is a curved surface that we can't use the approach we've done so far. So far with the flat surfaces, what you'd do is you would, if it was inclined, find the depth of the centroid, and then you'd find the inclined depth of the centroid, then you'd find the YCP distance, and so on. There's some of that in problems like this, but we've got to combine 2 different ideas together. We have to combine vertical forces and horizontal forces to find the net resulting force on a curved surface. So the types of problems we're going to solve, you'd be given a drawing like this, and then they'd say find the magnitude and line of action of the hydrostatic forces acting on the surface. And since this is just a cross-sectional view, this curved surface would go into the page, and so it would kind of look like a sheet of metal maybe that somehow got bent into, just by inspection, what looks like a quarter circle. So when you're faced with a problem like this, some of the questions you should ask yourself as you deconstruct the geometry that's in the image is, what's the shape of the curve? Sometimes it'll look in the picture like a circle, but it's actually a sphere. Or sometimes it'll be a hemisphere. You know, it would be a sphere cut in half. And so you may have to go to the back of the book to look up some of the volume formulas or some of the area formulas. Those are provided in the back of the textbook. One of the important questions is, how deep is it to the curved surface? And why do you suppose that's important to know the depth to the curved surface? It's to find the pressure. And so just when we had flat surfaces, for example, we wanted to know the pressure at a certain location because that's what the force depended on. And it's the same thing here. You want to find out what depth is involved so you can find the hydrostatic force that's acting horizontally. Finding intersection points is going to be important because the way that you'll solve problems like this is you'll break the shapes up into simpler components, because we don't have a ready formula for a shape that looks like this. We don't have the formula. I don't even know if this kind of a shape has a name, but I know that this kind of shape has a name. And that's a rectangle. And this shape has a name. It's a quarter circle. And so we're going to break complex shapes up into individual pieces that are easier to find volumes and forces related to, and the radius of the curve. So, for instance, now I've put some dimensions on that same drawing. And so the questions I told you to start to ask. Number one, we can see that that curve is defined by a quarter circle, and it has a radius. And so the distance from B to C and the distance from A to C is the same. The radius of curvature is 2 meters. And that dimension isn't up, it's up here at the top, but that's also the distance BC. All right, so now the depth to where the curve begins is important. The 4-meter dimension gets us from E to B. And then when we think about the projection of this curved surface is where we're going to find the depth to the centroid of the projection in just a moment. The radius of curvature, 2 meters, is what we're going to know to get down to the centroid of the projection. And then the original image that was given to you didn't have a lot of extra labels. And so you're going to have to, when you're presented with a picture, come up with some sort of a naming system so that you can refer to element B, C, D, E, for example, or element A, B, C. And so here, these relevant points have been labeled. And so that's just kind of a process that you can go through when you have a picture of something, is breaking it up into shapes, looking at the dimensions, and applying labels to points of intersection. Any questions so far? All right. So the question asked, what force is required to hold the plate steady? This external force F that's shown outside of the gate. And why would we have to apply an external force to hold the gate steady? Well, it's because there's water above the gate. And water has mass. It's heavy. You can think of it as the pressure is pushing on that gate. And if there isn't some force resisting that pressure, the gate's going to simply fall out of place and all the water's going to spill out. So we want to find out what's the magnitude of force required to hold that gate in place. And it partly depends on the weight of the water in element A, B, C. That's here what W is saying. It partly depends on the weight of the water in element B, C, D, E, because that water is above the quarter circle element and it's cumulative. But then also there are these horizontal forces that are acting from the left, and they're pushing on the gate as well. And so you'll notice that this force F is at kind of an angle. It's not straight up. We have to counteract the vertical forces and the horizontal forces. So the line of action, or the angle that this force is at, partly depends on the relative magnitude of the horizontal to the vertical forces here. So there's two vertical forces that are going to come into play: the vertical force of the rectangular element and the vertical force of the quarter circle, and putting those two together will be the vertical component of F. And then the horizontal component of F will be equal and opposite to F sub h, as is shown here. All right. Now, I think it's sometimes educational to ask you to speculate on things, because it maybe gets the critical thinking wheels rolling a little. So notice this from the picture. F sub v, the location of it, just by inspection, it looks like it's halfway between B and C. But what do you notice about the location of W? It's off-center. It's not exactly in the middle between B and C. All right, so it's subtle, but it is a little bit off-center. Is it shifted to the left or to the right of center? Why? Why is it to the left? There's more water on the left than there is on the right. Yeah, I heard somebody say centroid. So the center of area of a quarter circle is where they've located that force. And so the location of W isn't going to be just right in the middle here. It's going to be shifted over a little bit. And I'll show you a formula for the center of area of a quarter circle. But what makes these problems sometimes complicated is locating the forces. Just like how what made the hydrostatic forces on flat surfaces complicated was the trigonometry, right? I mean, it wasn't the fluid mechanics. It was remembering sine is opposite over hypotenuse, 3, 4, 5 triangle. It was that kind of slowed you down a little bit on the flat surfaces. Here, the tricky thing where it's easy to get mixed up is the location of the forces. All right, so here's what we're going to do. We want to find the magnitude of the vertical force Fb, the magnitude of the horizontal force F sub h, the weight of the water, and then the resultant F. Now here it's telling us that the force, that the surface AB goes 1 meter into the paper. So now with that 1 meter dimension, now we can start thinking in terms of volumes. You know, the volume of water in B, C, D, E. And if you know the volume of water, how do you get the weight of the water? If we have, so weight is volume multiplied by unit weight, right, gamma. All right, so that's the procedure that we're going to go through here. Now, let me tell you how to do F sub h, and then I think the rest of it you can do independently and is pretty straightforward. Now, F sub h, what we have to do is we have to envision the vertical projection of the curved surface. So AB is this quarter circle curve. And I said we need to think about the vertical projection of it. So imagine if there was a light over here, so a little light bulb, all right, and it's shining light. The shadow that would be cast by that curved surface, what shape does that shadow have? It's going to be a rectangle. And what will be the dimensions of that rectangle that the shadow casts? It's going to have, let's see, the height is 2 meters, right? From A to C is 2 meters. So here's the 2 meter dimension, and then 1 meter is the depth that's specified up at the top here as the given length of the gate. So what we're going to do to find F sub h is you pretend like there is a flat plate there, a vertically oriented flat plate. Hey, vertically oriented, we love those, right? We love vertically oriented shapes because they're so easy to solve. The depth of the centroid, the magnitude is equal to the pressure at the centroid multiplied by the area. The location is just YCP and so on. So let's do that. Let's find out F sub h. F sub h is simply the pressure at the centroid multiplied by the area. So the centroid I'm talking about is the center of area of the projection. So the vertical projection to find the horizontal forces. That's, I think, one place that students kind of struggle with is they see F sub h and they think horizontal projection. But no, it's the horizontal forces are acting on a vertically oriented projection. And so here, the way that we do that is we need to find the depth of the centroid, first of all, the delta H. So from the water line down to the location of the centroid on the projection is 5 meters, because it's 4 meters from the water surface from D to C, and then it's another 1 meter down to get to that location here, 1 meter. All right, so delta H is simply 5 meters. And so the pressure at the centroid, we'll do the delta H times gamma times area. Okay, so it's 5 meters depth of the centroid. The gamma here, we're not told explicitly that it's water. I'll tell you now, it's water. Okay. 9810 newtons per meter cubed, and then the area. And again, this is like the place where students sometimes make a mistake, is they'll say, well, is it the area of the quarter circle? No. For these horizontal forces, we're only thinking about the projection, the vertical projection. And so the area that we talk about in this formula is the area is 1 meter wide by 2 meters tall. So it's going to be 2 square meters. Okay, so 2 meters squared. So the horizontal forces end up being 98100 newtons. So those are the horizontal forces that are acting on the curved gate, but we calculated them by envisioning the vertical projection of that curved surface. All right. Now, F sub V and the weight, those we're just going to, yeah, go ahead.
The FA, is that force acting on the centroid of that square surface?
Good question. So you're asking where is that force located? It's not acting on the centroid. It's going to be lower than the centroid. Yeah. And it's not actually acting on the projection. It's acting on the curved gate. So we calculate the location and the magnitude of the force by considering the projection, but the force itself, that projection is just an imaginary thing. It's not actually there in the water. But this process will allow us to calculate the magnitude and the location of it by assuming the projection is there. Thanks for asking. That's a great question. Yeah. So the force is down below. So we could find the location of it by the YCP method if we wanted to know its line of action. And we'll do that in an example here in a moment. For the rest of this example, I'd like you to calculate FV and W. And now what I mean here by F sub x is, I mean, for this force that's shown, this force here, F sub x is going to be the horizontal component of F, and Fy is the vertical component. It always drives me nuts that I can't draw on this nice screen like I used to be able to draw on the whiteboard when I project, but F sub x is the horizontal component of F, and Fy is the vertical component. All right, so I'm going to pause the recording, give you a few moments to calculate FV, W, and then the rest of Fx, Fy, and F. We won't do on this problem 7 and 8. We'll tackle those issues on a different example. All right, I put the solution up on the board here on the screen. So the horizontal part we already did together. The horizontal force should be 98,100. And then just to reiterate, what we're doing is we're taking this curved shape and finding the vertical projection of it and then pretending as though there are some forces acting only on that vertical projection. So that's why the delta H is 5 meters, is the depth of the centroid for that vertical projection is 5 meters. Okay, now on this figure, F, V, and W, those are both just water weights. And it's unfortunate. Maybe it would have been more clear if it was W1 and W2, but anyways, the labels that were given in the text are FV for the weight of the water in element B, C, D, E, and then W for the weight of the water in that quarter circle. All right. So FV is relatively straightforward. It's just a box. You can think of it as like a box of water that's 2 by 1 by 4. How much does that water weigh? The other one, the weight W, that's a little bit more complicated. So it's a quarter circle that's projected 1 meter into the page. So the way that you find the weight of that is the volume of that multiplied by the unit weight. And so it would be the face area of the quarter circle multiplied by 1 meter of depth into the page. So the area of a quarter circle is 1/4 pi r squared. Anybody else get these same numbers, 78,000 and 30,000? Okay, good. So then the sum of the forces, we've only got one force that's acting in the horizontal direction. So F of x is going to be equal to, but with an opposite direction, of the F sub h that we had indicated before. So you see in this drawing I've done these components. So F sub x is the horizontal component of the resulting F that has to be applied to hold the system in equilibrium. F sub y is going to be the sum of those two vertical forces, the weight of the water above the curve. So the 78 was for the rectangular element, the 30 was from the quarter-shaped element. So if those are the component forces, then the net resultant force in the F direction we can find by taking the square root of the sum of the squares. So I got a question as I was walking around. Why don't we just find like the actual forces that are acting on that curved surface? And what makes it challenging is that along the curved surface AB, not only is the pressure increasing as we get deeper, but the direction of the force is changing as well. Up here near B, the forces are mostly to the right, so they're mostly horizontal. But then by the time we get down to A, the forces on that curved shape are mostly down. They're normal to the direction of the gate. And so rather than integrating a varying increasing pressure over a changing direction, the simplest approach is just to break it up into components. And that's what this does. In the end, once we get the vertical and the horizontal components, then finding the force required to hold the system in equilibrium is relatively straightforward. Are there questions on this example before we move on?
Could you just scroll back up to
Sure.
W real quick?
Yes. Doing a little sketch for yourself, I think, is the key to avoiding mistakes sometimes, even if it's as bad as this. And I can't imagine any of you would draw a shape as bad as this, but I mean, it gets the point across, right? That is it's a three-dimensional shape, and we need to find the weight of water that's in that shape. Any questions? All right. So here's another curved gate. This one's curving into the water. So I guess convex instead of concave. So in this question it asks how much force is required to open the gate. So we've got a lot of different ideas here. First of all, we're going to have in the end like a moment analysis problem where we've got F acting up at a 3 meter moment distance with B being the point of rotation. Now what's resisting that gate from being opened is the fact obviously that there's some water above the gate pushing down. Can you begin to think about breaking that up into shapes like we did on the previous problem? Like there are going to be vertical forces and there are going to be horizontal forces. The weight of the water above the gate is only part of the story. We are going to calculate that. We are going to calculate how much weight of water there is above the gate, but we're also going to have to take note of the horizontal forces because those will also be acting in the counterclockwise direction and resisting the gate from opening. So the horizontal forces. Okay, now what about the vertical projection of the curved surface? What does that vertical projection look like? What is the shape of the vertical projection? It's a rectangle, good. And the dimensions of that rectangle are what? 3 by 4. So it's going to be 3 meters tall and 4 meters wide are the dimensions. So we've got this imaginary rectangle in the water that we're going to find the depth of the centroid, delta H. Once we know delta H, we'll find the pressure at the centroid, P bar. From that, we can find the magnitude of the horizontal force, F sub H. And then in this problem, we are going to need to know the location of the force because that is going to factor into the moment analysis that we do at the end. And so actually when you're doing the vertical projection, we're going to want to know where the force is located for the horizontal forces. Okay, so let's do this. Let's consider breaking it up into pieces. Let's call A the element of water that goes from B over here to the edge and then up again. So we're going to calculate the weight of the water to find those vertical forces in element A. So that is a box of water that's 3 meters wide, because here's this 3 meter dimension down here from A to the radius, the center of the quarter circle. So that gives us the 3, and then it's 2 meters, and then in the previous slide it said it's 4 meters into the page. And so we can find the volume of element A. But the volume of water immediately above the gate is a little more tricky because it's actually not a quarter circle, but it's a rectangle minus a quarter circle is how much water is there. So look here at B. We've got B is this element from the edge down and over, but we are going to subtract out the quarter circle. So it's actually C that we want to know the weight of the water in element C. All right, so the location of the vertical force in element A is just in the middle. But the location of the force in element B is going to be a little bit more tricky because we're going to have to subtract out it would be in the center of B. We're going to do a weighted average where we find the magnitude of the weight of the water if it was all B, and then the location if it was a quarter circle. The center of area for a quarter circle follows the formula 4 times r divided by 3 pi. So here the radius is 3 meters, but the location of this, let me write that on the board, the weighted average, how we kind of handle that. All right, so the vertical force location. Basically, what I'm going to do is show you a couple of hints and then pause the recording, give you some time to calculate the actual numbers behind it. So the vertical force location, we're going to say that the two components are the quarter circle and this element C. And if you add those two things together is where you get B. And the overall element B is in the middle. The resultant force location is in the middle. So if we add the two components together, it should end up with whatever B is. So the volume of that is how we could think of it. The volume of element B acting at 1.5 meters from the edge is going to be equal to the volume of element D, the volume of element D, and that's going to be acting at 4r divided by 3 pi. That's how far it is from this edge to where the force is located, plus volume of element C multiplied by, that's the unknown. We're going to call it xCp of element C. So that's how we find out the location of force C, is we say we know that the overall net resultant force is 1.5 meters from the edge because it's going to be in the middle. And we know that element D, which is a quarter circle, has this formula that helps us to find the location of the center of area. And so therefore we can find the unknown location, this question mark here that's shown. We find it by the weighted average approach. Now, as it ends up, someone a couple of semesters ago went out and found a formula online for whatever this shape is called, where you subtract out a quarter circle from a rectangle. And if you want to find it, that's great. But if you want to have the tools to be able to find the location of the force for any kind of a shape, then this is the method that you can use for that. All right. So here's what I suggest you do, the process that you can follow for this example. First of all, we're going to find the horizontal forces. And then find the volume of all of these, the elements. So volume of B, volume of D, the volume of C. If you know the volume of B and D, then you can get C by just subtraction. B was the overall combination of those two pieces together. So volume C is just B minus D. All right? And then the force of element C is just going to be the volume of element C multiplied by the unit weight of water. So for horizontal forces, find the magnitude and the location. And by location, what we want is the YCP. All right, so I'm going to pause and give you a moment to start wrapping your head around this problem. There's a lot of pieces to the puzzle, so this is an important one. We'll take some time to get it right. All right, so we've got basically three pieces that we need to keep track of: A, C, and D. And C and D together are this element B. So here's element B. It has two components. So here in this solution, what I've done first of all is started with the weight of the water in element A, which is that rectangular element that's above the hinge. So it's a 2 by 3 by 4 shape, and once we find the volume, just multiply it by unit weight to find the overall force acting downward. Hopefully, if nothing else, hopefully you were able to get the force, the weight of the water in element A. Did everybody else get 235 kilonewtons? All right. Now the location of it is 1.5 meters from the left edge. And so what I'm saying is this 1.5 meters, we know the location of it is just going to be in the halfway point between the overall width is 3 meters, and so it's located, since it's a symmetrical shape, in the middle. Yes?
So when you're finding all the forces, you treat everything like it's its own block.
Yeah.
And then you just assume, like you just assume it's about the centroid, like for FA, like you just assume it's in the dead middle.
Yeah, it is. Yeah, because, well, the center of area for a rectangle, the placement of the center of area when we're thinking about its horizontal location is halfway between the two edges. So since it's a symmetrical shape, the center of area, and therefore the center of that force, is halfway between the two edges.
So then, like for like the C shape,
yeah,
wherever that is, you just find the force of that shape.
That's right. And so the force of the shape is going to be proportional to its area and proportional to its volume. So you'll notice here on this slide, I was giving you this weighted average system sort of on the basis of area, but on the board, I wrote it in terms of volume. It's because we're finding the location of that force by doing a weighted average, and it doesn't matter if you average it on the basis of force, area, or weight, because the ratios are the same. The ratio of the volume to D to the overall volume of B is the same as the ratio of the areas and the ratio of the forces. So the whole reason why we did this part of it is to find out where is the force located. So you see this question mark M, how far from the right edge, because we need to know the moment distance in the end.
The force of H is equivalent to what left?
The force, the horizontal forces?
Well, yeah, like how you have the...
Yeah. So here, F sub H is the horizontal force. So remember, there's the vertical forces, which are due to like these elements of water, the weights of this water above the gate, but then the horizontal force is when we think about the imaginary vertical projection of the curved surface.
Which in this case, you just assume it's like a square,
It's going to be
rectangle or something.
a rectangle because it's 4 meters wide and 3 meters tall. Yeah. Great questions. All right. So let's look back here. Okay, so we found the weight of element A. It's a vertical force. And now to find the weight of element C, we say it's the weight of the overall rectangle minus the quarter circle. So we don't have a specific formula for the volume of this shape, but we do know the formula for a quarter circle and the formula for a rectangle. So this shape is a rectangle minus a quarter circle. That's what B minus C is saying. And so the overall force of C. Any question about that idea of finding the properties of C by subtracting B and D? Okay. And now the location of the vertical force is when we apply this weighted average. And what the weighted average is acknowledging is, let me just briefly flip back to the projector here. All right, B If it was just a rectangle, then its force would be in the middle. And so the two pieces, when we combine them together, their combined force location has to be in the middle. So the quarter circle is a little bit to the right of center. This is going to be to the left of center. So when you combine those two locations together, their average location is in the middle. So I want to find out, if I know the average location is in the middle, and I can find the magnitude of B, then we can find the unknown one by this weighted average. Any questions about this part? All right, now the horizontal forces, it's the vertical projection of the curved surface is a 4x3 rectangle. And I think there were more than just a few people who, when they took the area moment of inertia, didn't remember that the projection of it is a rectangle, because it's so easy to make the mistake of thinking about quarter circles and then you take the area moment of inertia of a circle. So the shapes can be a little bit tricky. So that's why here we're doing AB cubed divided by 12, as it's the vertical projection that I'm doing all these calculations on. So delta H is equal to y bar, since it's vertically oriented. I can find the magnitude by doing the pressure at the centroid multiplied by the area. And then the location, the YCP, tells me how deep from the water surface that force is located. And that is 3.714 meters. Okay, so then the final step to find the force required to open up this gate, which is what it's asking, if we wanted to know what is F required to open up the gate, then we have to do the moment analysis. And so F is causing the gate to rotate in a clockwise fashion, and the moment distance is 3 meters. So I say 3 meters times F is going to be counterbalanced by the three forces that are acting on the gate. The force of the water that is in element A, the force of the water that's in element C, and the force that's the horizontal forces. And then we have to make note of their locations relative to the hinge. So in the case of the horizontal force, even though YCP is 3.7, the moment distance is 1.7, because it's a distance of 2 meters from the water surface to where the hinge is. Do you guys have a question?
He was just wondering about the YCP and why that was the 1.7 instead of 1.7.
Yeah, it's because the water surface to the hinge is 2 meters. So you subtract out that 2 meters and then you're left with 1.7. Okay, so in the end I think you should get a force of 412 kilonewtons required to open up that gate. Yeah?
You can use the centroid of that shape for the vertical forces, like what you use for the horizontal forces.
The centroid of this shape?
Yeah. You apply the vertical force there, why
Mm-hmm.
you use that height.
Because the horizontal force depends on more than just that shape C. The horizontal force depends on that shape C, and then also how deep under the surface that shape C is.
That's not taking into account whatever you did the rectangle on top by itself.
No, not the location of the horizontal forces. We need YCP for that. All right, so one last thing I want to tell you about when it comes to these forces is, let's say that we had an irregularly shaped gate like this. The force required to keep that gate in place is equal to the weight of the water above it. But sometimes we'll have gates with nothing above it. And so we ask, how do we find the magnitude of the force that's acting upward on the gate? Well, what you do is you'd extend the water line sideways, and that's the weight of the water that would be above it if there was water above the gate. And so the magnitude of the forces acting upward on this surface AB, it's equal to the weight of the water that would be above it if it was submerged. So you see this, this volume that would be filled is how you'd find the magnitude of the vertical forces. All right, I've got a couple of key idea slides that I want to show you just to help you get a jump start on the homework problems. And the first of them is for problem 388. They tell you L is 1, so that's the distance into the page. They want to find the magnitude, location, and the direction of the forces acting on the gate. So this is the same process that we've been through today. You want to find the vertical forces and the horizontal forces. But there isn't a weight of the water above the gate, but you can apply that idea that I just showed you on the previous slide of the weight of the water that would be above the gate. So here the vertical forces are going to be the water weight that would be above here if you extended A up to the water surface. And so there's going to be two shapes there, a rectangle and a quarter circle, that you have to find the volume of water above the gate. And the location, you're going to use the kind of weighted average approach that we introduced today over here, where we know that the location for the rectangle will be in the middle. The location for the quarter circle, you can find the centroid of the quarter circle with 4r divided by 3 pi. Tells you how far from the edge it is to the location of the centroid. And then the resultant you find by the square root of the sum of the squares. You can also find the angle that the force is applied at by the ratio of the horizontal to the vertical forces will tell you the tangent of the angle. All right, so this I think is really closely consistent to what we solved today, with the exception of this new idea of the weight of the water above it. The last one is there's a plug in a hole that's holding back water from leaking out. And there's this hemisphere. The head of this plug is hemisphere shaped, and so think about if you cut a basketball in half. You know, it's not just a half circle here, it's a half hemisphere. So when you calculate the vertical forces, the key here is the vertical forces that are acting upward on this piece, they're equal to the weight of the water that's displaced by the piece. Because this hemisphere is pushing water out of the way. And so the water is resisting that by pushing upward with the same magnitude of the weight of the water that's been displaced. And so you'll need to take note of the overall volume of the hemisphere for that. But then for the horizontal forces, you have to consider the vertical projection of a hemisphere. And the vertical projection that counts is the vertical projection that has the radius of the O-ring, because if we zoom in on the edge of that part, I want to show you that here's this part. Okay, there is a little bit of water that's acting that way until the O-ring occurs. And then there's a seal. Let me make the O-ring a little bit better. Here's a seal. So that there's no water below the O-ring. It's dry, but above the O-ring there is some pressure that's resisting. And so when you find the projection of that part, it's going to be the net projection, meaning where there's no water on one side but there is water on the other. So the 0.2 meters that they give you, that's the radius of the circle, that's the projected shape of the hemisphere. But on this problem, they do not ask you for the location of the forces. They're just asking for the magnitude of the horizontal and vertical. All right, that's all I have for you today. Just as a reminder that the assignment you should be working on, you've got some extra time for that, but It's better not to procrastinate. Get these done as soon as you know how to do them, and then they'll leave you plenty of time to study for the test.